All right. In this presentation, I'm going to talk about Linux, what it is, where it came from, and why you should care. Um, yeah, let's get started. What is Linux? Well, Linux is a free and open source operating system. It's licensed under the GNU GPL version 2, which is a open source license. And it's the focus of this class. It's what we're going to be discussing. Um, where is Linux? Well, it's found in almost all of the top performing supercomputers. It's the operating system of choice for most embedded systems. If you're using an Android phone, you're running a Linux kernel behind the scenes. Most of the computers that are powering the internet and other critical infrastructure. Um, Not that many home computers, unless you're going to count Chromebooks or the Valve Steam Deck, which are both actually running a Linux kernel. Um, Obviously, it's available on kernel.org as source code that you can download. Who is Linux? Well, in the beginning, there was Linus Torvalds. He created Linux in 1991 while he was studying computer science at the University of Helsinki. It was a personal project. Originally he was really only aiming to support his own software, excuse me, his own hardware with this operating system. He wanted to write something that would take better advantage of the new 386 chip that he had recently purchased. And this is a great quote here. It will probably never support anything other than AT hard disks, as that's all I have. End quote. This is from mailing list. And obviously it's gone on to do much more than that. It's has some of the greatest hardware support. It runs on almost everything. And it's obviously it's now a critical part of the modern world. And Linus Torvalds, he also ended up creating Git, which we also many people use for other purposes, but it was originally created just to act as a version control software for the kernel. But now, Linux is much more than Linus Torvalds. I mean, he still is the top guy. He still is in charge of the final yes and no decisions of approving, merging code. But at this point, it's a massive open source community project, probably the biggest, I would say. Thousands of individual contributors. A lot of development is also done by corporate sponsors, including Red Hat. And there's the Linux Foundation, which is a sort of organization that aims to promote Linux, but also to like organize this community project, and also to work with corporate sponsors. So why should you use Linux? Well, I mean, you don't have to, right? But I'm a fan. Linux is free software, and this is free as in free speech. You can do with it as you please, and there are uh, some advantages. No spying, no telemetry, adware, etc. At least in any mainstream Linux distribution. Compare that to any of your other choices for an operating system. Um, and yeah, you can expect and change any of the code as you wish, because almost all of it is free and open source software that you can contribute to. Um, so you can trust what you're running. It's fully customizable. There are different choices for things like the desktop environment or GUI programs, all the way down to exactly which version of the kernel you're running, which C library you're using, etc. Lots of these things are used on. There are lots of choices you can make. The Linux system is made out of lots of pieces. We'll talk more about that in a second. Um, and you can run it on less powerful computers. I think a lot of people have been able to revive sort of previously dead computers that were essentially end of life and could barely boot Windows XP or whatever. And they're happily running Linux and are actually usable by using something more lightweight. Um, so yeah, talking about that modularity, the being an open source operating system, with lots of community projects, when we're working on things, the entire tapestry that is Linux is made out of many pieces that are interchangeable. The kernel, the thing that really is undeniably Linux, is actually a relatively small piece of the whole bigger picture. Um, Distributions of Linux, also called distros, they sort of come with choices for some of these pieces. That's primarily what they exist to do, is so that you don't have to assemble all the pieces yourself, put them together, and make a system. You just download an ISO image, put it on a flash drive and boot into it, and they have compiled and selected a version of the kernel, various other things, your desktop environment if you have one, things like the package manager they'll use to manage software and get updates, default applications that might already be installed, and some other more technical choices. So Yeah, we can talk, about the differences that we'll see between distros. So there may be differences in package naming conventions. For example, on like Debian based system, um, if you wanted to get some library named foo, it would probably be called libfoo, dash dev. If you wanted to get like the version that you can use to link with, for your code. Whereas like on a Fedora like system, it's the same library, but it might be called libfoo dash devel. Or if you want the web server, I think it's called Apache 2. The package name is Apache 2 on Debian systems, Debian-based systems, whereas I think it's called HTTPD on DNF. But again, it's the same. They're both the Apache web server. It's just different package names. Um, there are differences in the target audience, right? There are distros that target servers or cloud computing versus, desktop or home computers. There are, targeting different people who are interested in gaming or people who are interested in software development. There are lots of reasons people are drawn to Linux. And so there are like tons and tons of different distros that cater to these different things. Of course, there are also differences in philosophy. Some Linux distributions or distros are designed to be very easy to use with lots of sane defaults that sort of make it quick to get up and running. But there are others that are designed, so that you can pick every single piece, put it together yourself, and make it, totally customized. Um, another area of philosophy is the accessibility of proprietary software. There are distributions that focus on offering only free and open source software so that you can sort of trust everything that you're running, versus others that make it easy to access some proprietary software as sort of a necessary evil for convenience sake. So whatever, the distribution that we're primarily using in this class is Fedora. I would say that it's, one of those ones that's mostly about free and open source software. It targets different things. I mean, we're using the Fedora server version, but they also have desktop ones. I think that probably put it more on this side, but I think there is some support for people who are doing cool stuff with gaming on Fedora. And yeah, whatever, we've talked about this. Another classic choice is Ubuntu. It's a Debian-based distribution, and many people's first introduction to Linux. I have nothing bad to say about Ubuntu, but I don't know. I just think that I don't know. I just prefer Fedora. What can I say? Arch Linux is another sort of famous option. It's one of those ones that you can really get in there and customize to your heart's content. Just be careful that you don't break anything. And of course, Red Hat Enterprise Linux, that's a huge distro in the sort of server space, and the enterprise computing. Used on lots of important servers and whatever. And whatever, it's a product. Uh, yeah, so to go a little bit deeper, we're going to talk about all the pieces of the system here that come together to form sort of the experience of running on a computer. This is sort of showing the boot process, or at least showing like the different levels that are involved, this sort of system stack. So when you like power on your computer, there's some hard-coded reset logic that reads data from an EEPROM, and it eventually runs sort of a UEFI sort of I don't know what the right word is, but a UEFI uh, system. Essentially, this is like the most base level of the functionality of your computer. This stuff is stuff that you're really not changing, and this is all really before Linux, right? And this is shared, whatever that, if you're booting between Linux and Windows, this part of it is all the same, right? Um, but then once you get a little bit further with something like Linux, you'd use a bootloader, right? That will actually get the operating system set up. Common bootloader that we use with Linux is Grub. I mean, there are other options, but most people are using Grub. Um, and so sort of the combination of the bootloader from Grub that can read the kernel and get the data, combined with information about the hardware that comes from the UEFI sort of pre-boot environment, including information about the hardware in the form of either a device tree or ACPI tables, that sort of describe what the system components are. These things are essentially passed off to the Linux kernel, right? We are whatever the bootloader loads the Linux kernel, gets this data, puts it together, starts running the Linux kernel. At this point, this sort of dividing line here, right, is the difference between the stuff that really isn't Linux, is before Linux, and this point, this is Linux, right? And the Linux kernel boots up, but obviously without anything running on top of the Linux kernel, you don't really have a system. So obviously there's levels above this. Essentially we have C shared library, like the C library or other shared libraries, and system calls that we can use to directly interact with the kernel. And then obviously we need to mount various file systems to access data or run programs. And then like once all of this is set up, we can actually start running a program, in the Linux user space. And the first program that ever runs is your init system, usually systemd. It runs as PID1, process ID1, the very first program. And it creates all of its children are the entire process. Every sort of running process in the Linux system can trace its sort of parentage back to PID1, the init system. And at that point you have a fully functioning system. The init system will set up some sort of login thing, and then you can start a shell, or you could log in using SSH. Then you'll have like an SSH program that's listening, and it'll accept a connection, and you'll get logged in, and then you'll be running your shell, and then you can run programs. And the programs the programs will be children of the shell. The shell will be children of the login process, and the login process will be a child of PID1, the init system, for example. And so at this point, this is a brief overview. We'll talk more about each of these pieces. This is not necessarily going to make sense immediately. We'll come back to this slide at the end, and maybe it'll make more sense. But okay, so we'll skip over most of this stuff because this is really like specific to your exact computer, how exactly this works. But the bootloader at Grub, it is not not part of Linux, but it is an important piece of booting. You may have seen this menu when you reboot your VM. It will, say Grub at the top. There'll basically be this sort of drop down where you can flip between options using the arrow keys. And these are essentially showing you things you can boot into, usually kernels, right? And so we had to go into here and actually select our new kernel during the E0 assignment. And yeah, I mean, it basically, Grub's job is to load the kernel into memory and start executing it. And, it contains the minimal amount of sort of code itself to be able to receive stuff like keyboard things to make these selections, and the minimal amount of code to be able to mount file systems to read, the kernel off of disk. And then it just puts that into memory and starts executing it, right? And that's primarily what the bootloader is for. So kernel, the kernel is the Linux kernel. This is a sort of a famous copy pasta, meme sort of text about the relationship between Linux and the rest of a system. Talking about GNU/Linux or GNU plus Linux, and the extent to which what we think of as Linux is, the Linux part of it is maybe only a small part. Pretty much everyone calls it Linux at this point. But Linux is really not actually that big of a part of it. I mean, the kernel is of critical importance, but it is actually not. Most of the software is not the Linux kernel. I mean, I don't know exactly what metric you want to use, but the Linux kernel is maybe only a couple hundred megabytes or something, on disk, and all the other stuff is, probably several gigabytes. And I don't know if you want to count lines of code. I bet that the Linux kernel is maybe higher by that metric, because not all of that code actually gets compiled into any given Linux kernel that you're running. But yeah, I mean, it is the at the very bottom of the stack, but it is not actually the entire system, and there's so much more on top of there. It essentially mediates access to the system's resources, right? And it sort of allows you to have things like protections, or sharing data, in a controlled way, so that programs can't corrupt each other's memory, users can't overwrite each other's files. Only the Linux kernel is able to directly interface with the hardware, with the CPU, with the disks, etc. And it sort of allows access, according to various policies that are configured, and this allows you to have the experience of using a system, and trust that there's not, some virus or something running on it that's, totally corrupting memory or hacking your data or something. Of course, these things are possible, right? But it's you need to find a serious vulnerability in order to exploit something like that, or you would need a to run a malicious program, right? And even then, it would be limited, right, because of the policies that if I run a virus, as my user, unless they can find a way to sort of escalate its privileges to the root user, then, for example, other people's files are going to be safe. There's no way for other people's files to get touched by something that's running as me, unless I'm the super user. Okay, so then the next big piece is the C standard library. it contains functions like printf, for example, but it also contains wrappers for system calls. So if I open up a terminal here, right, and I look at like man to write, write to a file descriptor versus man 3 write. Yeah, I guess it doesn't have one. Let me see if there's one that has a good example. Man to I mean, so the section 2 ones, right, in the manual, these are things for system calls, basically, and these are the direct ways that you interface directly with the Linux kernel. Whereas the section 3, so if we look at like, I don't know, man to clone 3 or something, these are whatever. This is the underlying function that's actually used on Linux to create a new child process. When we use the fork call right behind the scenes, we're actually making a call to clone one of these functions. And some of these, for example, there actually is no way to directly call this clone 3 system call. You have to use this special generic wrapper that's called a system call function. That allows you to just take a number and system calls just have numbers and it's able to execute that one. But there is no way to there's no clone 3 function. There's just this wrapper. Whereas if I look at like man 3 clone, there isn't one. I'd have to use something like fork or whatever if I wanted to create a child process, or pthread create or something, right? These are ways that I can create new processor threads. Whereas the underlying way in Linux is using the clone system call. And there's essentially there's a difference, and it sort of provides a compatibility layer, right, where you can write programs for a given version of the C library, and it can actually run on different Linux kernel versions, and depending on features that are added or not, present, depending on the version of the Linux kernel you're running, the C library has a more stable interface that maybe can stay the same as Linux changes below it. And it also has code like printf, right? So printf is part of the C library, and it's not a system call, right? Like it's only in the C library. And so there's tons of stuff, in section 3 of the manual, hundreds and hundreds of C functions, etc. These are all provided as part of the C standard library. And yeah, I mean, this is just an example showing actually the memory mapping of a process. This is actually looking at the process, a shell process. We'll talk about what's going on here maybe a little bit more later, but just the upshot here is that we're looking at the list of regions of memory, right, and their permissions and their size, essentially talking about different pieces. And so, for example, this was a bash program, right? I was looking at the memory map of a bash program, and so part of it is literally the executable code, right, from user bin bash, which is where the actual program lives, and that was mapped directly into memory, right? Then there's area like the heap, right, where we're allocating data, like with malloc or whatever, right? And there's the stack where all of our function call data, our automatic variables that are allocated in the stack are living. But right here, there's actually another section of the memory that's dedicated to mapping in this libc.so file, which is a shared library similar to a DLL. If you've used a DLL on Windows, if you've heard of a DLL, dynamic link library. But yeah, so it's a shared library, and essentially this code is getting added to my program. When bash was compiled, it says I need functions from the C library, and actually each time that one of these programs gets spawned, instead of each thing that's using the C library containing all of this code inside of it, right, which would make each of the binaries bigger, they each just say I need the C library, and then there's just one copy of the C library that each process gets mapped into memory. And this has resource benefits, in terms of the resource utilization on the computer. And again, the C library is just a useful compatibility layer between your operating system and your programs that you want to run. Yeah, and so there are other shared libraries right here. Just an example of the C library is the most important shared library, or most important library that exists. But the bash one also had this libtinfo. I think that's probably terminal info that deals with how different terminals operate, what maybe escape codes and things are needed to make them clear the screen or move the cursor or whatever. And this LD Linux, this is actually the dynamic linker itself, which it's its own sort of shared library, which is weird to think about. But these are just examples of shared libraries that are other ones that are sort of the backbone of a process. Then we have the actual like physical storage. So we have like block devices. I ran the lsblk command, and this is showing the various block devices. I'm not sure what this is, but I think this might be like potentially like the is some stuff related to the boot process. This is actually swap, right, which is essentially a portion of the disk that is set aside for storing memory, so that the operating system can actually use more memory, more physical memory than it has. Um, it can have mappings for more a larger amount of memory than you have physical RAM, and pages that are being used can actually be put on the disk temporarily inside of swap. These are kind of special cases, but here's the main thing that we're talking about. So we have this disk here, dev VDA, and it's actually broken into three partitions, right? And those are different sizes. And this one is mounted in slash boot. It contains information about like the bootloader, the Linux kernel, etc. Whereas this one is actually shared. It's this thing called a subvolume where it's actually mounted on both slash home and slash. There's sort of two different pieces of it. Um, but this these block devices, they are essentially regions of the physical hard drive that we can read and write data to, and they have a file system on them that the Linux kernel can then mount, and it's able to read this data off the drive. And then when we interact with files within the Linux kernel, there is a piece of the Linux kernel that is a driver for this particular type of file system that is able to translate the things that we're doing into how the data is actually stored on disk. Cool. And then yeah, the last thing maybe just talk about is the general idea of the file system layout. See also the file system hierarchy, which is a sort of standard for these things. So at the very top is slash, right? Slash is the root of the file system. It's sort of where every path begins. And then there's lots of subfolders within the slash directory. Slash root is the home folder for the root account, the super user account. Slash bin is often where command binaries are run. Example would be like the ls program. If I run the command which ls, user bin, it's actually in user bin. But there are, I guess if I look in slash bin, what do we have in here? Okay, so in this case, it's actually just assembling on my system. It's actually just assembling to user bin. But yeah, so there's binaries inside of there. Boot contains information about the bootloader, like grub or the Linux kernel or other things that it needs. Slash dev contains device files, so we can see on my system. I don't have the dev VDA 0, but this is sort of the um, there are like different partitions, right? And so each partition of my hard drive, if I look at lsblk, each partition of my hard drive, it gets an entry in dev/dev, but there's also stuff like slash dev slash null, which is a file that you can write to, and it will just sync arbitrary data. People often redirect the output of a command they don't want to get the output from into slash dev slash null to sort of suppress the output. Then there's other device files in there, and these are sort of created by the Linux kernel as an abstraction over devices that we might want to interact with. And we'll talk a lot more about devices and drivers and other things later in the course. But yeah, we'll talk about that more. But yeah, just device files live in slash dev. Slash proc is a really interesting one. We saw that actually earlier in this cat slash proc slash $$ maps. This is actually how we can view information about running processes. Slash proc slash and then the name, the process ID of any process will give you information about that process. And it's just great for being able to interact with other processes. And there are also things that you can do to access, for example, open file descriptors that you already have. It can be useful to reach into slash proc in order to get access to files that you've already opened. Like if you delete a file and you still have a program that has it open, it's actually possible to recover the data because it will still have an entry to it inside of its open file descriptor table, which you can find inside of slash proc. But yeah, okay. Slash etc has configuration files. And slash home has it's a folder that contains the home folders of all the users, and then slash lib has libraries. So that would be where like the C library might live. Yeah, so we can come back to this picture, and maybe it's a little bit clearer. We've talked about how Grub bootloader loads the Linux kernel and gets started. How the Linux kernel manages system resources and makes them available. How processes in the user space interact with system calls or the C library or other shared libraries, and file systems that are presented by the Linux kernel to create the software that we care about. Um, and yeah, so hopefully this is a little bit clearer. And really, all that's left is the question of the future. Where will Linux go from here? And I don't know. I think it's a bright future, and I think that well, hopefully you can be a part of it. By taking this class. Cool. That's all. Thanks for watching.